Okay, welcome back everyone. So I'm back on the board, so that's nice. So today we have a nice little integral for you here, and it's not really that little. And we're going to use Feynman's technique. So here's the integral. So the goal is to find the integral from 0 to 1 of sine of ln x over ln x dx. And here we have our little our complex definition of sine, and you can easily derive this from Euler's formula. And that's just sine of some z equals 1 over I times 1 over 2i times e to the iz minus e to the negative iz. Okay, so let's begin. So like I said, we're gonna just directly plug this into our sine function here and directly plug in our z as ln of x. Okay, because we just want to substitute an ln of x here in this case. And you'll see how this helps us when we're using Feynman's technique. So in other words, we just have that this equals the integral from 0 to 1 of, well, let's just directly bring the 1 over 2i on the outside, right, because we will have that there anyway. And then we directly have e to the I ln x minus e to the negative I ln x over, still have our ln x here, of course dx, right, and note that this equals, we have the 2i on the outside, 0 to 1, and if we kind of look at this, we bring the I into the exponent here by our logarithm properties, and we note that these terms just cancel out, just simplify as such. So the e and the ln cancel, and we basically just have e to the I, x to the I, minus x to the negative I over ln x. So this would be a perfect integral, or just really easy to integrate, since I negative I are constants. If the ln x wasn't there, then we could easily integrate this, right? Sadly, we have this ln x there. So somehow we want to create an integral so that our ln x here disappears, in a sense, and we're left with some nice and easy thing to integrate. So what we're going to do here is actually, for this to be nice, it's a better idea to actually take this 2i on the inside. Okay, so we have this 2i back on the inside. Okay, so let's let this integral be some, I guess, let's say some, I didn't think this through, I guess some k, yeah, we'll call it some k of, and it's actually convention that we have this little b here, and we have to parameterize this, so we'll let our b be here. Okay, so we're parameterizing this integral, and we have our b and our I here. And essentially the goal of this is to, like I said, basically if we take the derivative of this, we'll get some kind of easy thing here, such that if we integrate it, then we get something nice, and we can actually, well, integrate it and get our original k of b back as an actual, as an antiderivative, right? So, and note that this, we can take this integral here to be a special case of our k parameterization here. So in this case, this is k of 1, because we have our 1 here by the I, right? In this case, b equals 1, so b equals 1 in that case. Okay, so let's take the derivative on both sides and see what happens. So that was not nice. So we have k prime of b nothing but, okay, so on both sides we're differentiating with respect to b, so this is just d db, you can say, of k of b. We'll just write it as directly as our integral. X to the bi minus x to the negative I over 2I ln x dx. Okay, so this is what we have right now. And, okay, and whenever we take this db on the inside of an integral, it becomes a partial derivative. So we're taking the partial derivative of this stuff in the integral with respect to b. So let's see if we can work that out. So let's focus on the partial derivative. We'll say the partial derivative of, with respect to b, of x to the bi, this is just a lot of writing, minus x to the negative I over 2I ln x. Okay, so again, in the b world, we're treating this integral in the b world now. Sorry, not the integral, this partial derivative, since we're taking partial derivative with respect to b. So note that, well, in your head, you can kind of distribute the fraction here, right? So we're treating this entire part as a constant, but this part, if we split the fraction, we'll have this thing over this thing minus this thing over this thing. But this entire thing has no b in it, so that goes to 0. We want to focus only on the section with b in it, in a sense. So we're treating this as a constant here, and this is, okay, and we're differentiating with respect to b in this case, right? So in this case, we're looking for the partial derivative with respect to b of 1 over 2 I ln x times x to the bi, parentheses, of course. Okay, and we have to remember that we're differentiating this with respect to b again. So in this case, I is our constant, right? So x is a constant as well. And note that if we're, just in general, note that if we're taking the derivative of some a with respect to x, just as an example, or some a to x, by implicit differentiation, or logarithmic differentiation as well in this case, then actually this is nothing but a to the x times ln a. You can easily prove this to yourself. So just to clear some space, we're going to get rid of this because we're doing a lot of work today, and I'll probably split this up into parts, almost definitely. So we'll use this right here. We're using some chain rule and that. So this is our constant. We can set that aside right now and focus on this. Again, this is our constant here. So we just have that, well, this is equal to, this is equal to 1 over 2I ln x, and then times, okay, so we obviously have our ln x because that's our base and this is a constant. This definitely looks kind of weird. And notice that our ln x will cancel, and we'll see that how nicely that plays out in a second. Of course, times our x to the bi, right? So just all of that. But we mustn't forget chain rule. So we still multiply this by I. There we go. This cancels, this cancels, this cancels, and this cancels. So what we get in general is this integral. So we have k prime of b with respect to b. And and we'll directly pull out the 1/2 equals 1/2 integral from 0 to 1, and all we have here is x to the bi. Get rid of this. Okay. X to the bi, and we're still doing this with respect to x. So there we go. Assuming I've done all of this correctly, without mistake, this is what we're integrating. So, I mean, working out this integral isn't that hard. We're doing this in the x world, so we treat this as a constant. We just use power rule, we add 1 and divide by this stuff plus 1, right? So this equals 1/2 times, we'll do it in brackets, as such. Okay, so we just have x to the bi plus 1 over bi plus 1. And evaluate this from 1 to 0. X equals, of course, because this integral is in terms of x. So let's plug in x equals 1. Well, what do we get when x equals 1 here? We just get, well, okay, so that becomes 2, right? So plug in 1 here, this is always 1, 2, basically, and, well, we don't have to actually worry about that, so basically, yeah, there's no x on the bottom here, and we just get, assuming I've done this correctly, we just, okay, let's do this more slowly. So we just get 1/2 times, we get 2 over bi plus 1. So that's what happens when we plug in x equals 1, minus, we could put the brackets there, but we don't need to. We can just do this directly. And here we just directly get, well, plug in x equals 0. We simply, oh wait, sorry. I think I mistook this as the x being not in the exponent here. That's cost of sometimes having some bad handwriting. So yeah, let's redo that. So this entire thing in the numerator becomes 1, and so we just literally get 1 over bi plus 1, not even 2 up there, minus, and over here, plug in 0, that just becomes, yeah, that entire thing just becomes 0, so minus 0. So here we're just left with this, so we just get 1/2 times this, right? So that's what we're left with, assuming I've done that correctly. Yep, should be correct. That just becomes 0. Okay, good. So we have k prime of b equals 1 over 2 bi plus 1. So that's what we have here. But what we want to find in the end is k of 1, right? So let's integrate both sides. And obviously with respect to b, since we took the derivative with respect to b on both sides, so we want to get our original function back, and then plug in 1 and see what happens. So integrating on the left-hand side gives us k of b plus c, and we'll get another plus c over on the other side. But if we can think of it as plus some first constant plus second constant, bring the other constant over here and becomes another constant. So this accounts for that. And okay, that's pretty easy to integrate, right? We just get 1/2 on the outside, the integral, so the integral of 1 over bi plus 1 db, which equals, this is a linear function here, doing it with respect to b. The derivative of it is I, So don't forget the 1 over I on the outside of the ln. And we're doing the integral from 1 to 0, so we don't even need the absolute value. So we don't need the absolute value. So we have, 1 half times 1 over I just gives us 1 over 2I. 1 over 2I ln of bi plus 1. Okay. So now we have to figure something out to solve for that c, right? So let's try some stuff, okay? So let's see. Okay. So, well, we know that this, so this plus c, right, because this is our thing here. So we know that, well, 1 over 2I times ln of bi plus 1 plus some c, let's put that down, must equal our kb plus there, our kb over there. So we have integral from 0 to 1 of x to the I minus x to the negative I over, oh wait, we need our b there, of course, x to the bi minus x to the negative I over 2I ln x dx. Right? Okay, so let's try to plug in some kind of, some b where we can cancel everything out nicely and easily solve for c. So, well, let's see. So if we try plugging in b equals 0, we get this term must be completely 0, right? So that's nice. But if we plug in 0 there, we get some other messy stuff. We get 1 minus x to the negative I over all of that. And we still don't really know to directly integrate that. So what else? Well, let's see. So if we take, it's a bit tricky here. Okay. Because ideally we want b to be -1, right? However, let's see. So b equals -1 here, and then we have our I there. Okay. So b equals -1, but the nice thing is that if we have b equals -1, so take b equals -1, this might not be nice, that doesn't cancel out nicely, but if we have b equals -1 here, this stuff cancels, all of the numerator cancels, becomes 0, and obviously 0 over something, and we know that this is, the denominator isn't 0, so the integral of a 0 function is just 0, so this goes to 0, so this implies that, well, 1 over 2, this implies that this goes to 0, solve for c, we get c must equal -1 over 2I times ln, we plugged in b equals -1, I plus 1. Okay, so finally, our final answer amongst all of this mess will be, well, now we have our final form for our k of b. We have, again, looking back, we have k of b equals 1 over 2I ln of bi plus 1 plus the c, which is minus 1 over 2I ln of -I plus 1. So all in all, integral here. This integral, sorry for having such a small board, but oh well, which is k of 1 equals, basically, here, I'll leave this as an exercise to the reader because this board is actually getting too small. So, just basically try plugging in, so we've already done all the dirty work together. We've shown what k of b is. Just plug in b equals - 1, and you get the solution for our integral here. So hopefully you enjoyed that video, and have a nice day. Goodbye.